Today we are going to discuss the condition for equilibrium between phases or uniformity of chemical potential. Okay, now we will discuss chemical potential uniformity. We will multi-component, multi-phase system. Multi-phase, multi-component system. The chemical potential uniform other components all phases equally distribute discuss uniformity of chemical potential. Okay, here we are going to consider an important aspect regarding equilibrium between phases in a multi-phase, multi-component system where all the phases are in direct or indirect contact, so that any one component has the opportunity to found in any phase. Okay, so a multi-phase, multi-component system we consider multi-phase system component direct or indirect contact component phase equal distribute theory okay, derivation. Okay, for simplicity we shall restrict our discussion to two-phase multi-component system. Two-phase multi-component system is liquid. For example, two liquids layer two liquids contact liquids components distribution. Okay, consider a system where there are two phases, such a system in which there are two liquid layers, each phase containing a number of constituents. Okay, let the partial molar Gibbs energy or chemical potential of the constituent be mu1, mu2, etc. mu1, mu2, etc. are the chemical potential of the phase 1 and mu1 dash, mu2 dash, etc. is the chemical potential of phase 2. Okay, phase 2. Okay, suppose that there is a transfer of dN1 and dN2, etc. The moles of constituent from phase 1 and phase 2. dN1 number of moles in phase 1 and dN1 and dN2 is equal to number of moles of component 1 and 2, etc. Okay, then the change in Gibbs energy of two phases at constant temperature and pressure is given respectively by the equation. Okay, so here net changes are net changes dG1 is equal to mu1 dN1 plus mu2 dN2 plus etc. Equation 1 and dG2 is equal to mu1 dash dN1 plus mu2 dash dN2 plus etc. Okay, then the net change in Gibbs energy or dG, the net change in Gibbs energy or total change in Gibbs energy or dG of the above transfer process at constant temperature and pressure, we can return dG is equal to difference of these two Gibbs energy, that is dG2 minus dG2 minus dG1, that is equal to mu1 minus mu1 dash dN1 plus mu2 dash mu1 dash minus mu2 dash minus mu2 dN2 plus etc. Okay, for equilibrium to exist between the phases at constant temperature and pressure, we know that dG is equal to 0. Okay, now this equilibrium exists multi-component system equilibrium exists multi-component system equilibrium exists equilibrium at constant temperature, we can return dG is equal to 0. We can return dG is equal to 0. So we can write mu1 dash minus mu1 dN1 plus mu2 dash minus mu2 dN2 plus etc. is equal to 0. Okay, plus etc. is equal to 0. Okay, then since the transfer of each constituent from phase 1 to phase 2 can take place independently, okay, then dG at constant temperature and pressure for each independent transfer 2 must be 0. Okay, this means that each terms on the LHS of equation 4 must be 0. Each terms in the equation of the equation 4, each terms for since the transfer of each constituent from phase 1 to phase 2 can take place independently, then the dg at constant temperature and pressure for each such independent transfer 2 must be 0. This means that each terms on the LHS of the equation 4 must be 0. So we can written as mu n minus mu 1 dn1 is equal to mu 2 dash mu 2 dn2 is equal to etc. is equal to 0. Okay, this is the equation 5. Equation 5. Further, the dn1 and dn2 etc. are not 0. Hence, it follows that where dn1 and dn2 etc. are not 0. Hence, it follows that mu1 dash minus mu1 is equal to mu2 dash minus mu2 is equal to etc. is equal to 0. And then obviously we can return mu1 is equal to mu1 dash and also mu2 dash is equal to mu2. Okay, or general in any component at I in such system, ith component, either ith component mu I is equal to mu I dash. Okay. From equation 9, this is the equation 9. From equation 9, we can generalize that for equilibrium at constant temperature and pressure in a multi-component system consisting of number of phases, the partial molar Gibbs energy or chemical potential of each constant must be same in all phases. Okay, so chemical potential all phases same all phase component chemical potential same multi-component system. Okay, from equation 9 we can generalize that for equilibrium at constant temperature and pressure in a multi-component system consisting of a number of phases, the partial molar Gibbs energy or chemical potential of each constituent must be same in all phases. Okay, this is the uniformity of chemical potential. Next, we are going to discuss the Gibbs energy or Gibbs free energy and chemical potential of pure ideal gas. Gibbs energy and chemical potential of a pure ideal gas. Okay, one of the fundamental thermodynamic relationship that we have derived an earlier stage in this module used on several occasions is the one that shows the variation of Gibbs energy as a function of temperature and pressure. Okay, we Gibbs energy, temperature, pressure related in the equation. Okay, for the system undergoing a reversible change, dg can written as dg is equal to vdp minus sdt. We have a general equation, the Gibbs changing Gibbs energy and pressure and temperature. Okay, at constant temperature, since dt is equal to 0, at constant temperature, so we can dt is equal to 0, we can return dt is equal to 0. So dg can return dg is equal to vdp, dg can return vdp. Okay, let us take an ideal gas at 1 bar, the standard pressure at specified temperature T Kelvin. The Gibbs energy of the system is obviously G0, the standard Gibbs energy. Okay, suppose the pressure alone is changed, say P bar, so that the Gibbs energy changes to G at T Kelvin. We can integrate equation 2 between the specified limit. We can integrate 2 with specified limit G0 G. G0 G delta G is equal to G0 G delta G by the limit G0 G delta G is equal to integration of 1 bar, integration of 1 bar P bar VdP. Let us take an ideal gas at 1 bar, the standard pressure P0 at specified temperature T Kelvin. The Gibbs energy of the system is obviously G0, the standard Gibbs energy. Suppose the pressure alone is changed, say P bar, the Gibbs energy changes to G at T Kelvin. We can integrate. Now, standard pressure. ഒരു പി ബാർ പ്രഷറിലേക്ക് മാറുക. അതുപോലെ തന്നെ സ്റ്റാൻഡേർഡ് ഗിബ്സ് എനർജിയിൽ നിന്ന് ഒരു ജി അറ്റ് ടി കെൽവിൻ ഒരു ജിയിലേക്ക് ചേഞ്ച് ചെയ്യുക. അപ്പോൾ ആ ചേഞ്ചസ് ആണ് നമുക്ക് നോക്കുന്നത്. അപ്പോൾ സ്റ്റാൻഡേർഡിൽ നിന്ന് ഒരു ജിയിലേക്കും അതുപോലെ തന്നെ പ്രഷർ 1 ബാറിന്ന് ഒരു പി ബാർ പ്രഷറിലേക്കുമാണ് ചേഞ്ചസ് വരുന്നത്. അപ്പോൾ നമുക്ക് ഇങ്ങനെ എഴുതാൻ പറ്റും. ജി ഈസ് ഈക്വൽ ടു G0 at integration of G0 G dG and integration at limit 1 bar pressure to P bar. 1 bar is standard pressure VdP. Okay, then the bar shown in the above expression is to stress that the unit of pressure is bar. For an n mole of ideal gas, V is equal to nRT by P. Then the equation becomes G minus G0. അപ്പോൾ നമുക്ക് equation എന്താണ്? V is equal to PV is equal to nRT by PV is equal to nRT, where n is the number of mole, R is the universal gas constant, T is temperature, P pressure, P volume, and V is equal to n by P R2. Okay, അത് നമുക്ക് ഇവിടെ എഴുതാൻ പറ്റും. G minus G0 is equal to integration of 1 bar minus P and nRT divided by P dP. Okay, we can return as this equation like this. Okay, or we can return G minus G0 is equal to nRT ln P, or G is equal to G0 plus nRT ln P. Okay, G0 plus nRT ln P. Then this is the equation 5 and this is the equation 6. Then equation 6 shows that the relationship between G and G0 for an ideal gas. Rearranging the equation 6, we can get G by n is equal to G0 by n plus RT ln P. Where since the Gibbs energy per mole is regarding as chemical potential mu, equation 7 can written as 7, where G by n is equal to chemical potential or mu. So the equation 7 can be written as mu is equal to mu0 plus RT ln P. Okay, this is the finalized forms of equation 8. Here mu0 is the standard chemical potential, chemical potential at unit pressure 1 bar at specified temperature T Kelvin. Where P present a pure number because one cannot evaluate the logarithmic mode of administered quantities. Okay, which denotes the numerical value of pressure in bar. Okay, P represents a pure number which denotes the numerical value of pressure in bar. Okay, next we are going to discuss chemical potential of ideal gas in a mixture of ideal gas. Okay, now we are going to discuss the chemical potential of an ideal gas in a mixture of ideal gas. Chemical potential of an ideal gas in a mixture of ideal gas. Okay, in a mixture of ideal gas, the chemical potential mu I or ith component is given by mu I is equal to mu I0 plus mu I00 plus RT ln I. Mu I0 plus RT ln I. RT ln Pi. Okay, then Pi is the partial pressure of ith component. Then mu I0 is represent the standard chemical potential of ith component and Pi is the partial pressure. Okay, then if P represents the total pressure of the mixture and Xi is the mole fraction of ith component, Then we can written Pi is equal to Pxi, Pxi or Xi P, where small letter P is the partial pressure and capital letter P is the pressure. Okay, remember the partial pressure of the component in a mixture of gas is equal to the product of its mole fraction and total pressure. Okay, then we can written as mu I is equal to mu I0 plus RT ln XIP. XIP. Okay, then rearranging this equation, we can return mu I is equal to mu I0 plus RT ln P plus RT ln XI. RT ln P plus RT ln XI. Okay, the first two terms together on the equation of the equation. On the equation, this is the equation 1, this 2, this 3 and this 4. The first two terms on the equation to equation 3, 4. First two terms on the equation 4. The first two terms together on RHS of the equation 4 give the chemical potential of the pure component I under the pressure P bar. Okay, if this mu I pure is represented as mu I star. അപ്പോൾ ഈ ഒരു ടേമിന് മൊത്തത്തിൽ നമുക്ക് mu I pure എന്ന് പറയാൻ പറ്റും. mu I pure. അപ്പോൾ mu I pure നമുക്ക് mu I star എന്ന് represent ചെയ്യും. So this equation become mu I is equal to mu I star plus RT ln XI, where mu I star is the chemical potential of pure component. Okay, if the equation 5 gives the chemical potential of mu I of the component gas I in a mixture at temperature T Kelvin and a total pressure P bar. But okay, it can be seen that when Xi is unity, when only the pure component I is present, mu I is equal to mu I star. Okay, Xi unity ആവുന്ന സമയത്ത് നമുക്ക് പറയാൻ പറ്റും mu I is equal to mu I star. Mu I is equal to mu I star, which is exactly what we said just before the equation 5. Okay, in a mixture, however, since Xi is less than 1, its logarithm is negative. Hence, we can written as mu I less than mu I star, or mu I chemical potential is less than the chemical potential of pure component. Thus, the equation 5 shows that the chemical potential of any gas in a mixture is always less than the chemical potential of pure gas under the same total pressure. Okay, from the equation 5 shows that the chemical potential of any gas in a mixture is always less than the chemical potential of pure gas under the same total pressure. Okay, this is the chemical potential of ideal gas in a mixture of ideal gas. Okay, next we are going to discuss the chemical potential and real gas, the concept of fugacity. Okay, next we are going to discuss chemical potential and real gas. Fugacity. Okay, we know that the relationship between the free energy and the standard Gibbs energy for n mole of ideal gas is expressed G is equal to G star G0 RT ln P. Okay, where P represent the pure number which gives the numerical value of pressure in bars at T Kelvin. Okay, in order to preserve the same form of equation for real gas to a new function called fugacity. Okay, in order to preserve the same form of equation for a real gas to a new function called fugacity, which has a which has the dimensions and the general properties of pressure, has been introduced G. N. Lewis in 1901. One way of defining fugacity F is given an equation for real gas analogous to equation as shown below. G is equal to G0 RT ln F. Okay, അപ്പോൾ നമുക്ക് റിയൽ ഗ്യാസ് അല്ലെങ്കിൽ നമുക്ക് ഐഡിയൽ ഗ്യാസിന് പകരം നമുക്ക് റിയൽ ഗ്യാസിലേക്ക് വരികയാണെങ്കിൽ ഇവിടെ പിക്ക് പകരം നമുക്ക് റെപ്രസെന്റ് ചെയ്യുന്ന ഒരു ടേമാണ് എഫ്. Okay, in order to preserve the same form of equation for real gas to a new function called fugacity, which has the dimension and general properties of pressure, has been introduced by G.L. Lewis in 1901. അപ്പോൾ ഈ പ്രഷറിനെ പ്യുവർ റിയൽ ഗ്യാസിലേക്ക് വരികയാണെങ്കിൽ അവിടെ പ്രഷറിനെ റീപ്ലേസ് ചെയ്തിട്ട് വരുന്നൊരു ടേമാണ് എഫ്. എഫ് എന്ന് പറയുമ്പോൾ പ്രഷർ ടേമിനായിട്ട് ഇക്വലൻ്റ് ആയിട്ടുള്ളൊരു ടേമാണ്. ഓക്കെ, for changes of state at constant temperature and pressure in which G value changes from G1 to G2. Okay, and F value changes from F1 to F2. Integration of equation 2 to G1 to G2 and F1 to F2 we can represent delta G is equal to NRT ln F2 by F1. F2 divided by F for N moles. Okay, the effective pressure of the real gas, of a real gas is its fugacity, and hence it is also defined as F is equal to phi of P. The effective pressure at real gas is its fugacity. Real gas effective pressure എന്ന് പറഞ്ഞിട്ടുണ്ടെങ്കിൽ അത് അതിന്റെ fugacity ആണ്. So fugacity can be simply represent F is equal to phi of P. Where phi is a dimensionless constant called fugacity coefficient. അപ്പോൾ ഇതൊരു ഡയമെൻഷൻലെസ് ആയിട്ടുള്ള ഒരു കോൺസ്റ്റന്റ് ആണ്. അതിന് നമ്മൾ പറയുന്ന പേരാണ് fugacity coefficient. Phi is equal to fugacity coefficient. Fugacity coefficient. Phi can be simply represented. Phi is equal to F by P. Where fugacity coefficient of a gas in the ratio of its fugacity to pressure, or fugacity constant is the ratio of its fugacity to pressure. As pressure P tends to small value, a real gas tends towards the ideal behavior, and then F tends towards P. Okay, അപ്പോൾ pressure കുറയുന്ന സമയത്ത് as pressure tends to small values, the real gas tends to its ideal behavior. അപ്പോൾ low pressure ഈ real gas ideal behavior ലേക്ക് വരും. So F tends to P. Okay, the definition of fugacity for a real gas is then completed by setting the condition limit P tends to 0. F by P is equal to 0. F by P is equal to 1. Okay, അപ്പോൾ ഈ റിയൽ ഗ്യാസ് ഐഡിയൽ ഗ്യാസിലേക്ക് വരുന്ന എപ്പോഴാണെന്ന് വെച്ചാൽ റിയൽ ഗ്യാസ് പ്രഷർ കുറയുന്ന സമയത്ത് ഫ്യൂഗാസിറ്റി ടേം മാറ്റിയിട്ട് നമുക്ക് അവിടെ പ്രഷർ ടേം വരുന്നു. ഓക്കെ, ദ ഡെഫിനിഷൻ ഓഫ് ഫ്യൂഗാസിറ്റി ഫോർ എ റിയൽ ഗ്യാസ് ഈസ് ദെൻ കംപ്ലീറ്റഡ് ബൈ സെറ്റിംഗ് ദിസ് condition limit P tends to 0, F by P is equal to 1. Okay, the fugacity F may be regarded as a sort of frictious pressure or corrected pressure which applies to real gas. All effect arising due to the molecular interaction being obtained in the term. Okay, now the fugacity F may be regarded as a sort of frictious pressure. Fugacity is a frictious pressure or corrected pressure. ഈ പ്രഷർ ടേം കറക്റ്റ് ചെയ്യാനുള്ള ടേം ആയിട്ടാണ് നമുക്ക് ഈ എഫ് ടേം fugacity കൺസിഡർ ചെയ്യുന്നത്. ഓക്കെ, the fugacity F may be regarded as a sort of frictious or corrected pressure which applies to real gases. Real gas apply in the term. Okay, all effect arising due to the molecular interaction being contained in the terms. Okay, the fugacity is the pressure adjusted for the lack of ideality in a real gas. If a gas is behaving ideally, the fugacity is equal to the pressure. Okay, അപ്പോൾ ഈ ഒരു റിയൽ ഗ്യാസ് ഐഡിയൽ ആയിട്ട് ബിഹേവ് ചെയ്യുന്ന സമയത്ത് ഫ്യൂഗാസിറ്റിക്ക് പകരം നമുക്ക് അവിടെ പ്രഷർ കൊടുക്കാൻ പറ്റും, അല്ലെങ്കിൽ ഫ്യൂഗാസിറ്റി ഈസ് ഈക്വൽ ടു പ്രഷർ, ഫ്യൂഗാസിറ്റി പ്രഷർ ആയിട്ട് മാറുന്നതായിട്ട് നമുക്ക് കാണാൻ പറ്റും. ഓക്കെ, ഇൻ ഫോഴ്സിംഗ് ദ റിയൽ ഗ്യാസ് ബിഹേവിയർ ടു ഫിറ്റ് ആൻ ഇക്വേഷൻ analogous to one of ideal gas behavior, we have adopted one particularly. Okay, the standard state of a gas at any given temperature is taken as a state in which the fugacity and pressure are equal to 1. Okay, F0 is equal to P0 is equal to 1 bar. Since no real gas behave ideally at P is equal to 1 bar, this standard state is not a real one, but hypothetically one. For the convenience, hypothetical state are commonly used standard state. Okay, then for an ideal gas, mu is related to mu 0 by mu is equal to, for an ideal gas, mu is related to mu 0 equal to mu 0 RT ln P. Okay, then the fugacity is obviously related to the chemical potential of the real gas in the same way as the pressure is related to chemical potential of ideal gas. Okay, the chemical potential of pure real gas is then expressed in terms mu is equal to mu 0 RT ln F. Mu is equal to mu 0 RT ln F. F is the fugacity. Okay, where F is the fugacity of the gas, mu 0 is the standard chemical potential or chemical potential at unit fugacity, which is a function of temperature only. In a mixture of real gas, the chemical potential of ith component is given by mu I is equal to mu I 0 plus RT ln Fi. RT ln Fi, where Fi is the fugacity, the ith component, and mu I0 is equal to standard chemical potential of ith component. This is about the chemical potential and the real chemical potential and the real gas or the fugacity. Okay, then next we are going to discuss the concept of activity. Okay, then the certain purpose when dealing with solution of any kind, not only gaseous mixture but also liquid solution or the solid solutions, is convenient to define the quantity called activity. അപ്പോൾ നമ്മൾ ഈ പൊതുവെ ഈ ലിക്വിഡ് സൊല്യൂഷൻ പറയുന്ന സമയത്ത് അവിടെ പറയുന്ന ഒരു ടേമാണ്, തെർമോഡൈനാമിക് ടേമാണ് ഈ ആക്ടിവിറ്റി. Okay, the activity of a substance is a given state is defined as the ratio of its fugacity in the states to its fugacity in the standard state. Okay, the activity of a substance is in a given state is defined as the ratio of its fugacity in that state to fugacity in the standard state. So activity is equal to F by F0. F by fugacity to that state divided by fugacity its standard state. Okay, activity is a unitless quantity. Since for a gas, the fugacity in the standard state F0 is by definition 1 bar. Okay, the fugacity of a gas numerically equal to its activity. For a real gas, A is equal to F. Okay, since the gas, the fugacity in the standard state is equal to F0 is by a definition 1 bar. The fugacity of gas numerically equal to its activity. For a real gas, A is equal to F. So the activity of a real gas is given by A is equal to nu P. Okay, is equal to nu P. Then nu is a dimensionless quantity called activity coefficient. Okay, activity coefficient of a gas in the ratio of its activity to pressure. Ratio of its activity to pressure. In this case is obviously equal to 5, the fugacity coefficients seen earlier. Okay, appo ee oru case il namukku 5 is nu is equal to 5 namukku ezhudhan pattum. Okay, the chemical potential of pure gas can then expressed, chemical potential of pure gas Okay, and then expressed mu is equal to mu 0 plus RT ln A. RT ln A. Where A is the activity of gas and mu 0 is the standard chemical potential. So the chemical potential at unity, fugacity or activity. Okay, in a mixture of real gas, the chemical potential of ith component is then given by mu I is equal to chemical potential of ith component is equal to mu I0 plus RT ln AI. RT ln AI. Okay, when AI is the activity of the ith component and mu I0 is the its standard chemical potential. Okay, consider a process in which a system consisting of 1 mole of a substance, say a real gas, changes from a state 1 which chemical potential is mu1. Its Gibbs energy G1. G1 Gibbs energy since the quantity considered 1 mole to a state 2 with chemical potential mu2 and Gibbs energy G2. Here we can write. So, we change in system consider change in system changes 1 to system 1 to state 1 to state 2. State 1 la chemical potential mu1, state 2 la chemical potential mu2. Gibbs energy state 1 la G1, state 2 G2. അപ്പോൾ നമുക്ക് mu1 ഉം mu2 നമുക്ക് എങ്ങനെ എഴുതാൻ പറ്റും? 2 mu1 is equal to mu10 plus RT ln A1 and mu2 is equal to mu20 plus RT ln A2. Okay, then changes in mu or changes in chemical potential delta mu is equal to mu2 minus mu10 mu2 minus mu1 is equal to RT ln A2 divided by A1. Okay, well delta mu is the delta G. In this particular case, where the quantity considered 1 mole, delta G is equal to RT ln A2 by A1. A2 divided by A1. For 1 mole of ideal gas, we know that delta G is equal to RT ln P2 by P1. Okay, then a comparison of equation one, 2, 3, 4 and 5. A comparison of equation 4 and 5 shows that the pressure terms in equation 4 are replaced by the corresponding activity in equation 5. In other words, the activity is thermodynamic counterpart of its pressure. For n mole of gas, equation P may be modified by delta G is equal to nRT ln A2 divided by A1. N moles. Since activity is generalized concept applicable not only to gases but also to other systems. Okay, it is important that a description of the arbitrarily chosen standard state to which it refers should be given. Okay, it has already been mentioned that the standard state for a gas at any given temperature is taken as the state in which the fugacity and pressure are equal to 1 bar, or F0 is equal to P0 is equal to 1 bar. Since A is equal to F divided by F0, by definition this makes a fugacity numerically equal to its activity. For a real gas, A is equal to F. For real gas, A is equal to F. Activity is equal to fugacity. Okay. Ideal F dash 0 is equal to P dash 0 is equal to 1 bar. Okay. The standard state for a liquid at any given temperature is pure state of the liquid at 1 bar pressure. In this state, F is equal to F0, so that S equal to activity is equal to 1. Okay, in other words, in the standard state, the activity of liquid is unit. Okay, in the standard state, the activity of a liquid is unit. Okay, the standard state for a liquid at any given temperature is the pure state of liquid at 1 bar pressure. In this state, F is equal to F0, so that S equal to 1. Okay, in other words, in the standard state, the activity of liquid is unit. The standard state for a solid at any given temperature is pure state of solid at 1 bar pressure. In this state, S equal to 1. In other words, the standard state, the activity of solid is unit. Okay, then the activity of solid at standard state is also unit. Okay, this is the concept of activity. Okay, then the concept of activity in equilibrium system. Equilibrium system activity concept it is important to know that how the activity concept can be manipulated without distorting the theoretical validity according to the need and convenience while dealing with the equilibrium system. And knowledge would be particularly useful while we discuss the chemical equilibria in module chemical thermodynamics. Okay. Only a brief mention is made where without entering the theoretical discussion on it. Okay, we have already mentioned that the activity of thermodynamic counterpart of gas pressure. Okay, then in ideal system involving gaseous equilibria, the activity of each component gas is pure number, numerically equal to its partial pressure in bars. This is an aspect which is very important while dealing with chemical equilibria. Okay, in dealing with chemical equilibria in ideal solutions, the activity of a component can be taken as a measure of its effective concentration in the system. It can be conveniently considered as a product of concentration of the substance. Okay.